Our first speaker tonight is someone we are very lucky to have with us. In 2004, Astrid joined the original SRE team at Google, known at the time as the production team. As the SRE organization grew, she became the manager of the SRE team responsible for Google Web Servers, where she carried the pager for google.com for 5 years. For more than 5 years. Astrid spent some time managing the site reliability team for Google's social products before moving to the cloud platform team, where she led the development of the next generation Google App Engine. Today, Astrid is an engineering director, leading Google's search infrastructure teams. Please join me in giving Astrid a warm welcome.
So, as Chris said, my name is Astrid. These days I work in search infrastructure. I run the infrastructure components that do web searches, core web searches, middle tier. So effectively sort of the mixing and back-end communication layer for search. But I got my start in SRE, and I've been a site reliability engineer for a long time. I did that for about 8 years. And this is something that I think the definition of really evolves over time. I'm just going to talk a little bit about kind of where we started out with that and what it ended up looking like over the longer term. So what does it mean really to think about designing systems for the long term? In particular, in this talk, what I'm talking about is distributed systems. So spanning more than one machine, typically hundreds, thousands, tens of thousands, loosely coupled microservices-based architecture. This isn't something that we really had a word for when we started doing it at Google, and so we kind of had to figure it out as we went along. When I was putting this presentation together, I was sort of started out looking for the stereotypical like open road picture where you have the straight road going out to the distant horizon. And while I was busy looking for one of those, I realized that not only was it a terrible cliche, but it's also a horrible lie, right? Like no journey worth taking is ever a straight road with no obstacles. And when you start out building a very large scale system of any kind or anything that's big, you never know where you're gonna end up. So this is actually a picture of the Sacramento River emptying out into the bay. And it's pretty chaotic, but I think it's both really pretty and much more illustrative of what it looks like to manage large systems over time. So just to give a little bit of background, in 2004, I joined a small company. And Google at the time was actually really small. It was about 2,000 people total, about 500 or 600 in engineering. Probably actually like kind of relatively comparable to where Uber is at right now in terms of like a hockey stick on a scaling growth curve. It was also a company that did like basically one thing and did it really well. So this is Google before Maps. This was Google before apps. This is Google before self-driving cars. It's basically just web search and ads. And this was kind of an interesting time to join Google. The biggest reason being that it happened to be the point in time when we started rolling out the current generation of Google's large-scale cluster infrastructure, which for like 10 years I couldn't talk about, but now they published the Borg paper, and so that makes my life a whole lot easier when I give talks about things. This was the point at which Google was changing the way that it managed large-scale systems, going from managing individual machines and then sort of managing via Python script to managing in a distributed fashion. Switching from managing kind of machines and Linux kernels and so forth to managing things in layers. The Borg ecosystem is still the underpinnings of all of Google's distributed systems architecture. And it was kind of an interesting time because it was when we were talking about things like how do you manage your config files and what should we name them and where should we put them? And, should we all use one system or should we use lots of systems? And does it really all have to be in Perforce, or could we maybe use Git instead? And there like a lot of stuff like that. You can really spend a lot of time arguing about those things. But I think one of the biggest lessons over time is that none of that shit matters. What matters is that you agree on something and don't spend a whole lot of time arguing about it. So the first rule of managing systems for the long term is you have to assume you're going to be around. In its way, this is kind of an existence proof. Because if you're not around, then you're going to be looking for a new job in a couple years anyway. But should you happen to be wildly successful over time, you're going to have to live with the long-term consequences of the decisions that you make. And so, given that you never really know what the future holds, this is one of those things where you kind of need to just sort of show up every day, make the best possible decisions that you can, and think about, if not you, then at least someone you care about living with the consequences of the work that you do down the road. Now, every year, Google sends out a retention survey, and I always click, well, usually click, I'll probably still be here in a year. I always click, I will definitely not be here in 5 years. I've been wrong for some number of years. I'm coming up on 12, which is a very long time to be at one company. So, given that you don't really know what the future holds, the best you can do is kind of act as if you're going to have to live with it. One of the big rules of dealing with complexity is that it always increases over time. It's not really a symptom of success. It's not a symptom of failure. It's just that the longer you stick around doing work frantically year over year, month over month, week over week, the more shit you're going to pile up. And over time, left unmanaged, this makes it really, really difficult to move, to change anything about your system, to help it evolve, to change your product, to change how it operates. And so this is something where a little bit of investment over a long period of time can be really helpful. So the first thing that I want to say about managing complexity in systems is that at its heart, it's a people problem. The reason that you're managing complexity is because there's only so much that any given person can hold in their head. Now, the more complex the system is and the more people it takes to manage it, the bigger your teams need to be, the more of them there are. Every time you need to cross a team boundary to communicate something, you're getting slower. And so ideally, you're dealing with a situation where your teams can be doing more and more and more over time, which means the work that they're doing needs to get simpler. Each individual piece needs to get simpler, and they need to be able to focus on bigger and bigger and bigger picture. Also, hopefully your team's going to outlast any single piece of code. And so as much as you're worrying about the health of the system, you're also really worrying about the health of the team, right? You need to think about culture, you need to think about communication, how the team grows, how people talk to each other, how they work together. And the last thing is that it really is kind of the same as the first point, which is that adding scale shouldn't have to mean adding people. Your goal, particularly as an SRE team, but really as any engineering team, is to make sure that the system can scale exponentially while the team is scaling at a sublinear rate. You want the traffic graph to grow like this, and you want to see like no more than a recognizable number of new faces day over day, week over week. And the reason for that is really all about like human scale, mental scale. How many people can you talk to? How many people can you trust? Teams with trust move quickly. Teams with trust need to be relatively small. So I'm going to just talk a little bit about how systems grow and scale over time. And so typically, this is sort of obvious, but most systems start pretty small. You're starting at a prototyping phase. You've got like just a couple components typically talking to each other. They might even still be on the same box. And when your system's pretty small, this is a terrible time to think about really large scale infrastructure. I feel like this is one of the failure modes of infrastructure people coming into small, rapidly scaling companies, which is that too much infrastructure is just as bad as too little, right? Like when your system is small, you want to be able to be pretty reactive. You want to be able to have everybody working really closely together. And you want most of your people to really be focused on the work of building the system, building the products, those kinds of things. And so the other thing that I'm going to say is that this is true not only of your core systems, but of every new system that you build, right? All systems have a life cycle. Everything starts somewhere. So even if your main system is well past this phase, you're going to come to this place with every new system that you build. And that's a great place to, like a great time to think about the trade-off between sort of how much structure you want to impose versus, how much flexibility you're going to have. Some things that are really good to think about at this point that are very hard to fix later are some standardization and standard practices. So making sure everyone keeps their code in the same place, roughly, like just, even as broadly as saying like everyone keeps their code in GitHub is better than everyone keeps their code in like 15 different source control systems, whatever one they prefer. This is a great time to think about standard practices like code review. I'm a big fan of code review, and I actually kind of believe that it should always be a matter of policy for any company that is serious, particularly about reliability, but also about like not getting sued later. It's just generally sort of good practice to cover your back for a number of reasons. This is also a good time to think about whether there are any sort of standard underlying infrastructure components that are helpful to standardize on. Like one thing that Google did very well when it was small was it had a couple of basically sort of universally standard libraries that did things like always export a small HTTP server on a particular port that you could hit to figure out whether or not the system was up, whether it thought it was healthy, whether it was serving traffic. And that was like a really small piece of standardization, but it ended up being really important over time because as systems scaled, even though you might not even have heard of any particular system before, this comes up as a lot as an on-call engineer. Even in the best managed system, it's common to be paged by something you've never heard of. If you're getting paged by something you have never heard of, it's really helpful to have some basic standardization, some standard tools around like, here's where the logs are, here's how I know if it's up, here's how I know where to find the monitoring for it. Because you may find yourself at 2 in the morning troubleshooting from first principles for a system you've never heard of, and suddenly your whole system is down because of it. So this is a time when it's really great to sort of have a few standard practices around that. So over time, these things tend to diversify. And there's usually a couple of axes of scale to think about when you're thinking about how systems grow. Typically, people think about what I like to think of as vertical scale, which is, amount of QPS, number of instances, 100 QPS, 10,000 QPS, a million QPS, et cetera. And typically, you're just adding clones of a system at that point. But there's also horizontal scale, which is sort of organizational scale, right? The diversity of the systems that you're handling, how different the servers that your teams are managing are from one another, the sorts of things that they do, multiple teams interacting, figuring out what happens when you cross hops between different teams. Like, does every team have different production practices? Because that's overhead that you're going to be carrying as your system scale. And it might just carry on indefinitely unless you take a point at which you want to step back and just think about, like, what can we standardize? What's costing us pain? The other thing to think about is that even with vertical scale, even when you're just dealing with more instances, typically every order of magnitude comes with its own choke points. So, you go from 10 to 1,000 of something, how are you doing with sort of your thread pool connections to your front ends or your back ends? Are your logging collection mechanisms keeping up? Like, at every order of magnitude of scaling, something new breaks. You're not always going to be able to predict it. So it's good just to sort of keep an eye out for how your systems are behaving, and keep an eye out for like the little instabilities that crop up as things get bigger and more complex, because there's going to be themes. And every time you see those themes arise, that is an opportunity to respond effectively, or at least to begin responding to the sorts of problems of scale that you're starting to see. So during this phase, when things are diversifying, I think the most important thing to remember is that your goal is not to stop diversification. This is messaging particularly for ops teams, which can tend to be pretty conservative. Your goal is not to stop the growth of the product, to stop the number of new systems rolling out, to say like, oh, let's everybody put the brakes on and take a pause and figure out how to standardize all of this. Your job is to figure out how to roll with it. Your job is to figure out how to help your organization grow effectively and in kind of a managed way. And so this is something where at a certain point, I think it's impossible to manage this kind of scale without good tooling. So I mentioned the Borg infrastructure at Google. This is something that produced a really fundamental change in the way that Google operated. Right? Before Borg came along, people were managing individual machines, individual instances of things. And there were maybe, I think, probably less than 50 services, maybe less than 20, even sort of roughly defined. After Borg came along and abstracted a lot of the ways that people had to deal with managing systems, managing reliability, gave us the ability for systems to self-heal to some degree, like auto-replacing nodes. We saw a jump from tens to hundreds, thousands. I think today we're in the tens of thousands of services, might be hundreds of thousands of services. Like, it's really a hell of a lot. We saw this massive explosion, not only of the number of services that people were running, but of the kinds of things that people were doing, the speed at which they iterated, the amount of control that they could have over their own systems, and frankly, just an enormous explosion of the amount of innovation that they were able to bring to bear, because they weren't worried about all of the little shit that is easy to get caught up in when you're thinking about your job of system maintenance as like, I log into the box and I do the thing. Like I used to joke when I was on call, like I don't get out of bed for less than 10,000 machines. You don't want to ever care about an individual machine. So I mentioned environment standardization. That's true on the code level and sort of development practice level. This is also a good time to think about production environment standardization. And I think that we're in a good time for the industry now because there's a lot of really great tools present, which really only shown up in the last few years. Like now there are really, really good scalable monitoring infrastructures. There's good logs collection analysis tools, tools for managing configuration, for managing system lifecycle, all of those kinds of things. The thing I mentioned earlier about standardization, doesn't matter which of them you pick, and it's really easy to spend a lot of time arguing about it. Pick one, make sure everybody uses it. The goal for standardization within your engineering environment is that engineering teams shouldn't be spending a lot of time arguing about the tooling associated with their production environment. They should be spending a lot of time building their systems, building their products, putting the money where, putting their code where their mouth is, making sure that you're actually focused on building user-facing products. And on the flip side of that, the job of the operations team or the SRE team is to make sure that that tooling is consistently supported, that you have put enthusiasm, energy, backing, and infrastructure behind it, that you're providing good options to the teams that you're working with, and that you're listening to them about the things that they need. And so, during this period of sort of massive diversification where things are just getting more complicated all the time, I really don't think that there's a general rule of thumb about what to focus on in terms of optimization, except to keep an eye on what's costing people time. And you should consider cost broadly. It's very easy to get into a state where your engineering team is moving super, super quickly. They're building new things. New services go over the wall every week. But you're having to hire, tens, hundreds of ops people. That is not a win. Your company is still paying for all of those people. It's very hard to hire them. You're probably not getting an efficient organization out of it. And you're probably not building the kind of organization or system that you want to live with over the long term. So don't just think about the costs that your team is seeing. Also think about the costs that the organization is seeing. And be conscious of the fact that in a lot of cases, what looks like simplifying your situation is actually just moving complexity around. Think about reducing it within the system rather than moving it, and you're going to be better off. I think the single biggest rule of thumb here, and this is a really big sort of recurring theme, is to think about reliability, think about scale, think about complexity as an engineering problem. If you're thinking of it as an operational problem, then you're only moving the complexity around. You're not dealing with it. This is a case where if you bring an engineering sensibility to bear, identifying like what is complex, what's working well, what's not working well, and think about that in terms of like, is there a project that would fix this? Is there a system that would fix this? Like, what code changes could we make to make this work better? You're going to do a much better job of reducing costs overall. And the other thing is using shared infrastructure, if it's available, is often a way to drop cost. But as I'm going to talk about in a minute, there are additional and different costs associated with standardization. And it's worth thinking about the trade-off between those things. As you get to that point, as your system is growing and you're looking at the places where there's duplication, there's going to be a point where you need to make a decision about, for any given piece of functionality, whether it's worth it to standardize on shared infrastructure. This comes at different points in the life cycle to every system. But, if you're at a point where, let's say a team is rolling out yet another image processing pipeline, and you're asking things like, don't we already have one? And they say, well, yeah, but it's different. It doesn't do exactly what this one does. We need this one because it's different. It does something different. And you're like, well, there are 5 of them. Looking at the costs associated with that, like, okay, there's the amount of time it's going to take to build that. There's the amount of people it's going to take to build that. Who's going to be on call for it? What happens when all of those people have left and you have to figure out the long-term maintenance plan for like who takes that logic over? There are arguments to be made at this point for consolidating on one thing and making sure that it's flexible enough to meet the needs of the customers that might come along. This is a place where at Google, we had early investments in some standardized layers in key places. One of the biggest is the front end layer, which remains standardized to this day. There's some very nice talks about it, which you could look up if you wanted to, talking about the Google front end and load balancing layer. This is one that was always standardized at Google, even when pretty much everything else was going in its own different directions. The reason for that is that it is the very first line of defense in terms of reliability for the system as a whole. Like if that one is hyper reliable and you can load balance effectively, if an individual instance of something else goes down, then you've got this, you have an engineering solution to at least part of your reliability problem, which is, you don't have to worry about the failure of any individual instance or data center because you can load balance to something else. And so this is one where Google made early investments in reliability. And also early investments in shared infrastructure. There was another one that came along that my team was responsible for. It goes with this slide. Which is that for some number of years, my team was managing the Google Web Server. This had a couple of different components. One of them was the set of servers that serves Google's homepage. Also served a bunch of like random GIFs and Google logos and stuff like that. People would periodically send us requests for, I have like just 2 terabytes of data. I would like to put it on your servers. Could I do that? And we would always have to say no, because the way that worked is that we just had tens of thousands of instances of those web servers. And every 3 hours or so, we shipped them the whole tarball of their data all over again. So you couldn't put more data on that service than you could fit on a single machine, nor could you push more data to it than you could sort of reasonably push to thousands of instances within a couple hours. So that was a case where, this need came up periodically. And it wasn't a huge cost to any individual team when we said no. They would go away, they would write their own static content serving service, somebody would get promoted to senior engineer, and then, it would be like this small, maybe like 5 or 10% cost that every service at Google paid. But over time, it sort of occurred to us that this was a cost that everybody was paying. And it seemed like an opportunity, not only because it was a cost that everyone was paying, but also because there's actually a fair amount of flexibility that you get about being able to manage a layer collectively. And so what we were able to do when we built a generalized service was do stuff like offer standardized caching, great integration with our edge serving layer, standardized behavior around things like kind of fancier features like image processing and JavaScript concatenation and stuff like that. And it turned out over time to be reasonably useful to lots of people, so much so that it's now like, I think it's still 4 of the top 5 services at Google by traffic, which is easy to do with a static content system, but it also gives you a sense of the scale of the shared problem that we had been ignoring for a really long period of time. So there are times when there is a huge benefit to be gotten from something like this. The thing that I'll say about that is that it's a good idea to be conservative, because even the most simple example of a shared system, like the one that I just mentioned, it took 2 years to really get built out properly, built up, scaled out, built to be a multi-tenant system. And there's a fair amount of engineering that goes along with that. Shared systems are their own specialty. If you're building shared infrastructure, you need to worry about things like what happens when one user generates a whole lot of traffic on one particular shard, or what happens if a user accidentally overwrites somebody else's data. You need to protect the users from themselves. You need to protect them from each other. It's also not enough just to build it. You also have to worry about moving people over, because there is no road to hell more thoroughly paved than the road of systems that were built intending to build shared infrastructure that never got further than like 1 or 2 big services. I think I turned down 3 of them, 3 separate times at Google with different products that had inherited like the last known instance of like our write through caching system. The last known instance of I think I turned down iGoogle 3 times. I turned down FastNet a couple times. The abandoned shared system is far worse than the specific system. So this is something where, if you really think your team is going to make a commitment to doing this, think about whether or not you really are in this for the long haul. Because if you're not, just don't do it. And the other thing here, the last point on this slide is one that I think is sort of one of the most fundamental truths of any distributed system, which is that all systems must protect themselves. Like, this is how you engineer systems to be scalable. It's how you engineer systems to remove complexity. The system should protect itself from users. It should protect users from one another. At Google, all of our biggest DOS attacks always come from ourselves. The reason for that being, like, who's got really big systems and no protection against itself? We do. It is very easy to make a configuration error in one very large system that will throw all of its traffic at another very large system, especially if they're within the same network. And they may not necessarily have the same protection against, like, traffic overload that they would for external traffic, for example. This is something where you don't want to have to rely on human action to intervene here. The more a system is able to defend itself and behave well under stress, the less times you're going to have to get woken up in the middle of the night. So in the life cycle of every system, there comes a time when you ask yourself, is it time to start over? Cake or death? The answer is almost always no. People have different opinions on shared systems. I actually have a pretty strong one here, which is that whether you're starting over from scratch or you're starting over incrementally, if you have a large system that's doing something complicated and you need to do that differently, you're going to pay the same complexity cost whether you start over or whether you adapt the one you have. But the one you have is already doing a job. And typically, you are not going to find yourself sufficiently resourced to develop both systems in parallel for a long period of time. If you do decide that you need to replace an existing system, a few things that are helpful here, I think. One is figure out the smallest possible iteration of the change that you're looking to make. Get it in production early, test it early and often. If your new system doesn't unlock new capabilities, it is probably a bad idea. The reason for that is, a lot of times an engineering team will be looking at the complexity of an existing system and they'll say, like, my new one will be just like this, but it will be easier to change. No one is motivated to move to your new system, and it's probably not easier to change. It's probably just different. This came up there's an example that I really like for this one of iteration in place from the Google web server, which is now a very old example. Those single instances I mentioned were also single-threaded. And at a certain point, we were kind of taking a look at that, and I was kind of comparing it, the single-threaded web service that we were supporting, to the 32 and 64 core machines coming down the line, and thinking about the overhead of maintaining, 32 or 64 instances of a server on a single machine. There's a RAM overhead for every one of those instances. There's also the distributed systems kind of fan-out effect overhead for all of those instances. And so we decided, after some consideration, that the engineering team was going to make a really large-scale investment in multi-threading that system. And because that system was full of logic that they were afraid to touch, they decided to do it in place. So they spent, I think, about 2 years, one call path at a time, single-threaded to multi-threaded, single-threaded to multi-threaded, single-threaded to multi-threaded. On the day when we were finally ready to cut over and say that, like, we are a fully multi-threaded architecture, we're moving to a multi-threaded deployment model, bigger instances. That was about the same week that we hit the limit on our ability to add more instances behind the load balancing layer. Load balancing layer is like, no, go back and start over. Which would have been a hard break on our ability to scale Google's infrastructure, right? Like, no more web search for you, no more features. But happily, we had already made that 2-year investment. We really needed that new capability, and we were ready to cut over. And so there are times when you need to do this, and it's important not to overtrain on, like, oh, we can just use the one we have. Like, there are times to make a large-scale investment, and it's important to be willing to do that when you need to. But make sure you're setting yourself up for success if you do it. If you are building a new system, this is also one on which there's a bunch of schools of thought, but I'm also super firm on this one. Move the biggest customer first. The reason for this is that it's really easy to say, like, oh, I'm going to pick a medium customer or a small customer and move them over. and that'll be easier. It's almost never easier. You'll spend almost as much time moving your medium or your small customer as you will moving your big one. And if you don't start with the biggest one, it will never fit. If you want to build a race car, you should really not spend more than about 10 minutes building a cardboard box. When we rolled out the Borg ecosystem at Google, the first customer was web search. That was incredibly risky in the sense that like that generation of web search wouldn't have launched if Borg hadn't launched. It was all untried infrastructure. It was new architecture. Everything about it was new. But it fit those success criteria, right? Like we absolutely needed that new cluster system to go really badly. And we moved the biggest customer first. And after that, everybody was a pain in the ass, but it was a tractable pain in the ass. And so just in terms of sort of long-term rules for maintaining systems over time, given that you don't know where you're going, and it's really, really hard to plan ahead in an organized way, you want to be reacting to the situation as you find it on the ground, right? Like great rule of thumb, just like don't let the weeds get higher than the garden. Whatever is troubling you most today, spend some time investing in that, pay it down a bit, get on to the next problem. One of our longstanding rules in SRE was not don't get paged. It was never get paged for the same thing twice. Any failures that you're running into should at the very least be novel. It's good for the team, it's good for the system, and it means that you're growing as well. Invest in your support infrastructure. Monitor from a user's perspective. This is really important. That way you'll know if it's broken. If you know nothing else, you'll at least know whether it's up or it's down. And that is, at the end of the day, almost the only thing that you need to know because the rest you can figure out. Automate anything that you do more than twice. And the biggest one is the same as my first point, which is take care of the team. Right? All systems have finite life cycles. Everything has its season. But if you're doing a good job, if you're doing it well, if you're really maintaining your systems, investing in them, growing your systems and your teams over time, and not spending all of your time hiring replacements for the team that you've burned out, your team is going to be with you for a long time. And so you want to be thinking about how to grow that in a healthy way, how to manage that team effectively, how to make sure that they're facing new challenges, and how to make sure that they're focused on the stuff that really matters, right? Like you don't want to be in isolation from the important problems of the business, from the things that need solving. Because if you're not paying attention to that stuff, your competitors certainly are. And so at the end of the day, all of this is sort of about balancing the amount of time that you're spending on your product versus your maintenance overhead in such a way that it will allow you just to move as quickly as you need to move and to innovate at the rate that you need to do that. And so, there's not really a victory condition here, right? Like growing a system is always a long game. It's not about like, oh, I'm going to do it correctly. I'm going to win this argument that I'm having this week, and then everything will be great. We're going to win. It's really more about, showing up every day, doing some good work, making sure that the work is getting in front of the users, making sure that you're making your team's life better, you're making your systems better, and that you're making your users' lives, your customers' lives a little bit better. Pay attention to the complexity in your system. Keep half an eye on the details, but make sure that you're paying attention to the gain that you're putting into the world, and the rest, frankly, is just details.